Okay, let's jump straight into this explainer. Today, we're going to build a modern, autonomous humanoid robot from the ground up. For decades, the idea of a truly universal robot worker was pure science fiction. But right now, by combining these incredibly smart, glowing neural brains with highly adaptive mechanical muscle, that fiction is literally walking right onto the factory floor.
We are kicking things off with a massive paradigm shift. If you've been following robotics at all over the last few years, you've definitely seen the videos. You know the ones. Robots doing backflips, dancing, nailing parkour runs. Well, those days of heavily pre-programmed viral stunts are officially over. We're in a new era. As the industry shifts, machines like the 2026 Electric Atlas are stepping out of the lab and into real, chaotic environments to do unpredictable, genuinely valuable work.
So to really understand this shift, here's our roadmap. 1. We'll look at moving beyond the viral stunts. 2. We'll dive into the brawn, specifically reinforcement learning locomotion. 3. We'll examine the brains with vision-language action models. 4. We'll see how they go from simulation to reality. And finally, 5. We'll look at humanoids actually on the clock.
Okay, Section 1. Beyond the viral stunts and into the new era of autonomous labor. There is just a stark, night and day contrast between the old, brittle, hand-coded robots and these new, flexible, AI-driven machines. Take the old hydraulic atlas. It relied on something called model predictive control. Basically, engineers had to painstakingly write thousands of lines of code to define exactly how the robot should balance and move based on rigid physics equations. And if something unexpected happened, the robot usually just failed. But the new Electric Atlas is a totally different beast. It boasts 56 degrees of freedom, custom actuators that allow a 360-degree rotation of its torso and limbs, which is wild to see, and most importantly, it's driven by large behavior models and reinforcement learning. It isn't just executing a script anymore. It actually understands the physics of an object and adapts in real time.
Moving to Section 2, Brawn. Let's talk about reinforcement learning locomotion.
Picture this. A bipedal robot, like Cassie, is subjected to a push recovery test where it gets aggressively smacked with a giant wooden mallet. It's intense. Now, traditional, rigid math models completely break down when a robot gets hit unexpectedly like this, simply because the exact force and angle of that mallet strike were never pre-programmed. But by using a trained reinforcement learning policy, the robot can dynamically recalculate its center of gravity and recover its balance on the fly. It's essentially learning to react, much in the same way you or I would if we got shoved.
But here's the crucial point. This physical brawn isn't learned out in the real world initially. It would be way too dangerous, not to mention insanely expensive, to have multi-million-dollar robots just falling over and breaking repeatedly. Instead, they use a rigorous 3-step sim-to-real pipeline. First up, they simulate the robot in thousands of virtual environments, just randomly scrambling physics variables like gravity, friction, and mass. This is called domain randomization. Second, they use an algorithm called proximal policy optimization, or PPO, to train the control policy through literally millions of trial-and-error attempts. Only after the AI absolutely masters walking and balancing in these chaotic, completely unpredictable virtual worlds is it finally deployed onto the physical hardware.
Right, on to Section 3, Brain. Let's dig into vision-language action models.
The absolute secret sauce of modern humanoids is the vision-language action, or VLA, model. Think of this as the ultimate translation engine. Say a factory supervisor walks up and tells a robot to prioritize the heavy struts. Well, a VLA model is the glowing neural engine that processes those spoken words, visually identifies those specific struts in a cluttered bin, and translates that understanding directly into the continuous physical joint movements required to reach out and grab them. It's what seamlessly bridges the gap between digital reasoning and physical action in the real world.
And what's really fascinating here is how modern robotics is mimicking biological principles to pull this off. VLA models are increasingly using a two-stream processing architecture that's heavily inspired by the human brain. You have the ventral stream, which is all about semantic recognition, so identifying what an object is, like knowing the difference between a blue block and a red wrench. Then you have the dorsal stream, that handles spatial processing, knowing exactly where that object is in 3D space, which allows it to guide the robotic hand down to the precise millimeter for a perfect grasp. By explicitly separating the what from the where, the robot can handle much more complex and cluttered environments.
And researchers are constantly tweaking and optimizing these artificial brains. Recent empirical studies from the Cross-VLA project show that using advanced fine-tuning techniques, specifically a super-efficient method called DORA, results in massive jumps in a robot's success rate. By decoupling the magnitude and the direction of weight updates during training, researchers found some incredible optimizations. To put that into plain English, this fine-tuning basically acts like a highly targeted software patch, and it achieved a massive 10.4 percentage point gain across benchmark robotic tasks. That's a huge deal. It means these brains are getting drastically smarter and more reliable, and they're doing it without needing entirely new, massive models built from scratch every single time.
Section 4. Let's look at getting from simulation to reality.
The sheer speed of deployment we're seeing today is staggering. In the old days, if you wanted to teach a robot a new factory task, you were looking at months of manual engineering, custom coding, tweaking physical parameters over and over. Today, using stationary upper body setups like the Atlas manual task system, they just harvest massive amounts of manipulation data and feed it straight into the AI. Because the whole system learns through reinforcement learning rather than hard coding, a company like Boston Dynamics can fine-tune a working robot policy for a completely new task in just 48 hours. Literally over a single weekend.
Finally, Section 5, Humanoids on the clock.
Because make no mistake, this autonomous labor race isn't just happening in slick R&D labs anymore, it is happening right now on real factory floors. Figure 03 is already handling complex logistics sequencing at a BMW plant. The Electric Atlas is doing heavy-duty sequencing, moving actual engine covers and struts at Hyundai's facilities, and Agility's Digit robot, which was purposefully built for this kind of logistics work, is out there moving totes and bins at Amazon fulfillment centers. These aren't just conceptual pilots happening in a vacuum. They are actively integrated into real-world supply chains today. Now, pulling off this software convergence requires some seriously specialized hardware. Figure 03 is a prime example of this. To survive a grueling 24-hour shift, they redesigned it from the ground up. It now features advanced palm cameras, and you might wonder, why palm cameras? Well, when a robot reaches deep into a bin, its main head cameras get blocked. The palm cameras, combined with these new tactile sensors in the fingertips, keep the robot's brain fully informed entirely through touch and close-up vision. That specific hardware evolution is exactly what allowed Figure to recently demonstrate a 24-hour, completely unsupervised package sorting endurance run. But it's important to remember this tech isn't just for heavy industry and dusty warehouses. Look at the Fourier GR3. This is a fascinating pivot. It's a humanoid specifically designed as a care bot for elderly care and rehabilitation. It utilizes its 55 degrees of freedom and an incredible 31 pressure sensors across its body just to provide a safe, lifelike tactile response when it interacts with humans. It even uses a dual-path AI architecture, so it has a fast-thinking system for immediate physical reflexes, to catch someone or prevent a fall, and a slow-thinking large language model for holding natural, complex conversations with patients.
So what does this all mean for us? This convergence of advanced VLA brain reasoning and dynamic, resilient physical brawn marks a massive economic shift. I mean, we've gone from viral backflips to 24/7 unsupervised labor in just a few short years, which leaves us with a pretty profound question. As these machines completely shed their lab constraints and perfectly replicate human versatility on the factory floor and eventually in our homes, how will our global supply chains, our economies, and our workforce ultimately adapt? It's an absolutely fascinating future, and as we've seen today, it's arriving much, much faster than anyone thought.